Welcome. Today we're going to do something a little different. Let's put on our senior engineer hats and walk through a mock system design interview. The challenge? Designing an online bookstore from the ground up. This is a classic interview question, so if you're in the software world, you'll definitely want to stick around. Let's get started. So, picture this. You're in the interview. The interviewer slides a marker your way and says, "Design an online bookstore." It's a huge question, right? It's so easy to get overwhelmed, but don't panic. The key here isn't to magically have the perfect answer right away. No, it's about showing the interviewer how you think. And the very first step is to break this massive problem down into smaller, manageable pieces. Before we start thinking about all the cool stuff like lightning-fast search or handling millions of orders, we've got to lay the foundation. And in system design, that foundation is built with entities. Just think of entities as the nouns of our system. They're the core things that everything else is built around. Books, users, orders. These are our Lego bricks, and we're about to build our bookstore with them. Okay, so let's start with the most obvious entity, the book. It's a bookstore after all. Every book needs a unique ID, a title, an author, a price, but there's one more attribute here that is absolutely critical: stock quantity. We have to know how many copies of each book we have. This little number is going to be a huge deal later when we get into inventory management. This whole process, by the way, is called data modeling, and it's a crucial first step. Next up, what good are books without people to read them? We need our customers, or as we'll call them, users. And what do users do? Well, they shop. So naturally, we need a cart entity to keep track of all the books they're thinking about buying. The cart is basically just a temporary holding area that's tied to a specific user. Now, this is where it gets interesting. We have our Lego bricks, but now we need to define how they snap together. These relationships are the blueprint for our entire application. So think about it. A user has one cart. That cart can hold a bunch of different books. A user can also place many orders over time, and every single book stock level is managed by our inventory system. Getting these connections right is absolutely essential for building a system that actually works. All right, we've got our foundation in place. Now let's tackle our first big feature, search. If a user can't find the book they want, they can't buy it. Plain and simple. So how do we make searching for a book feel instantaneous, even if we have millions of titles? This is a really fun problem, so let's dive in. Okay, so the simplest, most basic way to do this would be to just loop through every single book in our database for every search. We call this an O of N operation, and trust me, it's painfully slow. A much, much better way is to use hash maps. Think of a hash map like a super efficient index in the back of a textbook. We can create one where the key is, say, the author's name, and the value is a list of their books. This gives us a direct, nearly instant lookup. Now, there's a trade-off. We use more memory to store these maps, but the speed boost for the user is totally worth it. All right, let's move on to one of the trickiest parts of any e-commerce system, and it's a topic interviewers love to poke at: inventory management. This is where things get really complex. It's all about one simple goal: don't sell a book you don't actually have. If we get this wrong, we're going to have some very, very unhappy customers. Let me paint a picture for you. We have one single copy left of a brand new bestseller. At the exact same millisecond, two different users hit the Buy Now button. Who gets the book? More importantly, how do we stop ourselves from accidentally selling it twice? This is a classic race condition, and it's a huge problem in distributed systems. So here's the danger. If our code first reads the stock count, which is 1, and then a moment later writes a new value of 0, both users' requests might read 1 before either of them gets a chance to update it. It's like two people trying to walk through a doorway at the same time. They both see it's open, but only one can actually get through. We end up selling the same book twice and breaking a promise to one of our customers. That's a big no-no. So how do we fix this? The secret sauce is something called an atomic database operation. Atomic just means it's an indivisible, all-or-nothing action. We can use a single SQL command that does everything in one go. It finds the book, it checks that the stock is greater than 0, and it subtracts 1. All while the database locks that specific row, preventing anyone else from touching it. The first request to run this command wins. The second one, it'll fail because the stock greater than 0 part is no longer true. And just like that, our race condition is solved. Whew! Now that we've solved that inventory nightmare, let's look at the bigger picture, the checkout process. This is where we bring everything we've built together and actually turn a user's cart into a confirmed order. So here's how it all flows. First, the user hits Place Order. We immediately validate their cart and run that atomic inventory check we just designed. If everything's in stock, we move on to processing the payment. Only after the payment is a success do we officially create an order in our system and mark it as confirmed. Then, finally, we kick off fulfillment, telling the warehouse to ship it and keeping the customer updated along the way. And if you're curious what this might look like in code, here's a simplified version. We'd have a book class, a user class that has a cart object inside it, and that cart would just hold a list of books. The order and inventory classes manage their own data. This clean, simple structure is what brings our entire system to life. It's pretty elegant, right? Okay, so far, so good. Our design works, but a really great interview answer doesn't just solve today's problem. It anticipates tomorrow's. What happens when our little bookstore becomes a massive success with millions of users? Our single application, what we call a monolith, is going to crumble under that load. It's a classic scaling problem, and it's something every senior engineer needs a plan for. The modern solution is to break our monolith into microservices. Instead of one giant application doing everything, we have a bunch of small, independent services. We'd have one service just for managing users, another for book data, one for orders, and so on. This way, if our payment service gets swamped, it doesn't slow down the rest of the site. We can scale each part of the system on its own, which is a massive advantage. But how do all these little services talk to each other without creating new bottlenecks? Well, that's where a message queue like Kafka comes in. Think of it like a central post office for our services. When an order is placed, the order service doesn't have to call the inventory service directly. Instead, it just drops a message in the queue. Hey, order 123 was just placed. The inventory service, the shipping service, and any others can just listen for those messages and do their jobs whenever they're ready, asynchronously. It makes the whole system incredibly resilient. So there you have it. That's a whirlwind tour of designing an online bookstore. But the most important thing to take away from all this is that there's no single right answer. It's all about showing your thought process. Did you talk about the trade-offs, like using more memory for faster search? Did you have a plan for scalability? Did you handle tough, real-world problems like race conditions? If you can demonstrate that kind of thinking, you're going to nail that system design interview. Now go out there and build something amazing.